Hello everyone, I am Dr. Manisha Verma from Acharya Narendra Dev College, University of Delhi. I have begun a lecture series on thermal physics. Today I will be discussing the kinetic theory of gases, a very important topic of thermal physics. What are the salient features of the kinetic theory of gases? First of all, this theory is applicable for ideal gases. It is a theory based on a simplified molecular or particle description of an ideal gas from which many important properties of the ideal gas can be derived. The British scientists James Clerk Maxwell and the Austrian physicist Ludwig Boltzmann in the 19th century established this theory, which became one of the most important concepts in the modern science. Such a model describes a perfect gas and is a reasonable approximation to a gas in the limit of extreme dilution and high temperature. It means real gases will also show kinetic theory of gases when the temperature is very high and the gas is extremely dilute. N by V is very much less than 1. Such a simplified and trivial description, however, is not sufficiently efficient to account for the behavior of gases at high density. Gases consist of atoms or molecules randomly moving around at high speeds. The kinetic theory of gases models the thermodynamics behavior of gases by linking the microscopic properties of the particles, that is, its mass and speed, to the macroscopic properties of particles, that is, the pressure and volume. Now let us briefly discuss the assumptions on which the kinetic theory of gases is based. First assumption: all gases consists of a very large number of minute rigid particles called molecules. The gas molecules are point masses and their actual volume is negligible as compared to the total volume occupied by the gas. Second assumption: the gas molecules are in a state of random motion in all possible directions with different velocities and collide with one another and with the wall of the container. Third assumption: the collisions between the molecules are perfectly elastic in nature. It means there is no loss of energy when gas molecules collide with one another or against the walls of the container. Fourth assumption: the collisions are instantaneous in nature. That is, the time of collision is very small as compared to the time between successive collisions. Fifth assumption: between two successive collisions, a molecule travels in a straight line with uniform velocity. The distance between any two successive collisions is called the free path. And if we take the mean of many successive collisions, the distance between them, it is called the mean free path. There is no effective force of attraction between the molecules and the walls of the container, the distance between the gas molecules being very large. Seventh assumption: the pressure exerted by a gas is due to the continuous bombardment of the moving molecules on the walls of the containers. Eighth assumption: the average of kinetic energy of the molecules is directly proportional to the absolute temperature of the ideal gas. Ninth assumption: there is no effect of gravity on the motion of the gas molecules. Tenth assumption: the number of molecules of gas in a container is very large, therefore average behavior is usually considered. Before beginning with the main plank of kinetic theory of gases, which is the Maxwell-Boltzmann law of distribution of velocities, first of all let us calculate the expression for pressure exerted by a gas. What is the cause of this pressure first of all? The pressure exerted by a gas is due to the continuous bombardment of the molecules of the gas against the walls of the container. Let us consider the motion of only one molecule because all molecules are identical in nature. Consider a gas contained in a cubical vessel of side L with perfectly elastic walls containing a large number of molecules N. Let C1 be the velocity of the molecule in a direction as shown. This can be resolved into three components U1, V1 and W1 along the x, y and z directions parallel to the sides of the cubical vessel. Then C1 square is equal to U1 square plus V1 square plus W1 square. Call this expression 1. The momentum of this molecule that strikes the wall ABCD of the vessel is equal to mu1, where m is its mass. As the collision is elastic, the molecule will rebound with the same momentum, that is mu1. The change in momentum due to the impact is equal to minus mu1, which gives us 2mu1. It strikes the wall LMNO and returns back to ABCD after travelling a distance 2L. The time between the successive collisions on ABCD, that is time for one collision, is 2L by U1. Hence, the number of collisions per second this molecule makes with the wall ABCD becomes U1 by 2L. The rate of change of momentum is equal to the change in momentum into the number of collisions per second, that is 2mu1 into u1 by 2L is equal to mu1 square by L. From Newton's second law, the rate of change of momentum is equal to the impressed force. Let us say this force is F1. Then F1 becomes mu1 square by 2L along the x-axis. Similar relations will also hold true along other directions also. Similarly, the force on another molecule of velocity c square, whose components are u square, v square and w square, due to impact will also be mu square by 2L along the x direction. Hence, the total force Fx on the face ABCD due to the impact of all the n molecules in the x direction will be given by Fx is equal to m by L u1 square plus u2 square plus u3 square plus so on so forth un square. Call this expression 1. Since pressure is nothing but force per unit area, the pressure Px on ABCD will be given by Px is equal to Fx by L square is equal to m by L cube u1 square plus u2 square plus u3 square plus so on so forth un square. Call this expression 2. Since P is equal to F by A and A is equal to L square, similarly, if Py and Pz are the pressures on the other two faces of the cubical enclosure, we get Py is equal to Fy by L square equal to m by L cube brackets v1 square plus v2 square plus v3 square plus so on so forth vn square. Let us call this expression 3. Similarly, we get expression for Pz. Pz will be Fz by L square is equal to m by L cube w1 square plus w2 square plus w3 square plus so on so forth to wn square. Call this expression 4th. As the pressure exerted by the gas is same in all directions, the average pressure P of the gas is given by P equal to Px plus Py plus Pz divided by 3. Average, we have to take the average of the pressure. So P is equal to m by 3L cube, L cube because of volume, into U1 square plus U2 square plus U3 square plus so on so forth, Un square plus V1 square plus V2 square plus V3 square plus so on so forth, Vn square plus W1 square plus W2 square to Wn square. Hence we get expression 6 as the expression for pressure of the gas. In this expression, we have clubbed U1 square plus V1 square plus W1 square in one bracket, U2 square plus V2 square plus W2 square in another bracket, and we have done this for all the cases. Since L cube is equal to V, the volume of the cube, we can write, instead of L cube, we can write V. Moreover, C1 square is equal to U1 square plus V1 square plus W1 square. C2 square is U2 square plus V2 square plus W2 square, and so on. We get P is equal to m by 3V C1 square plus C2 square plus C3 square plus so on so forth Cn square. Call this expression 7th. Now let us multiply and divide this expression by the number of molecules n. We get P is equal to m by 3V into n, C1 square plus C2 square plus C3 square plus so on so forth plus Cn square divided by n. Here C1 square plus C2 square plus C3 square plus so on so forth plus Cn square divided by n is C mean square. So what do we get? We get P is equal to m by 3V into n C mean square, where C mean square is known as the mean square velocity of the molecules. If m is the total mass of the gas, then capital M is equal to n by n into small m. N is the total number of molecules, m is the mass of each molecule. So capital M is small m into capital N. Hence we arrive at the result P is equal to capital M C mean square by 3V. It means P is dependent upon the mass of the gas. Now let us write the expression for pressure in terms of density. If rho is the density of the gas, then the pressure of the gas becomes P is equal to 1 by 3 rho C mean square. The root mean square velocity of the molecules is equal to the square root of the mean of the squares of the velocities of individual molecules. It is given by root of 3p by rho. In terms of the mean kinetic energy per unit volume E, the pressure exerted by the gas can be written as P is equal to 2 by 3 E, where E is equal to half into rho into C mean square. Thus we can say that the pressure of the gas is numerically equal to 2 by 3 of the mean kinetic energy per unit volume of the gas. A very important relation. Now let us study and discuss the kinetic interpretation of temperature. We have to derive the relation U is equal to 3 by 2 RT. The pressure exerted by a gas of n molecules occupying volume V is given by, as we have just seen, P is equal to m by 3V n C mean square. Here P is the pressure, m is the mass of individual molecules, V is the volume of the enclosure, n is the number of molecules. So rearranging the terms, we get PV is equal to m by 3 into n C mean square. If V is the volume occupied by a gram molecule of the gas and capital M is the molecular weight of the gas, then capital M is equal to m into Na, where Na is the Avogadro's number. So we get PV is equal to m by 3 C mean square. From the perfect gas state equation of state, we get PV equal to RT. Calling the earlier equations 1 and 2, from 1 and 2 we get m by 3 C mean square equal to RT, or m into C mean square is equal to 3 RT. Divide the whole equation on both sides by 2. So we get m by 2 C mean square is equal to 3 by 2 RT, or U is equal to 3 by 2 RT, where U is equal to m by 2 C mean square is called the internal energy or the average kinetic energy of the gas. If we divide both sides of equation 3 by Na, which is the number of molecules in 1 gram molecule of the gas or 1 mole called the Avogadro's number, we get m by 2 Na C mean square is equal to 3 by 2 Na into R into T. As capital M by Na is small m and R by Na is K, where K is the Boltzmann constant, we get half mc square is equal to 3 by 2 kT. So we have arrived at the result that the mean kinetic energy per molecule in a given mass of a gas is proportional to the absolute temperature capital T of the gas. This is a very important relation which the derivation of which can be seen from the basic assumptions of the kinetic theory of gases. Thus, according to kinetic theory of gas, the temperature of a gas is the measure of the average kinetic energy of the translational motion per molecule of gas. If T is equal to 0, then C mean is equal to 0. Now, what is the relationship between C RMS and C mean? C RMS is equal to root of C mean square, which gives us root of 3 kT by m. Pressure of a gram molecule of the gas is given by PV is equal to m by 3 Na C mean square, or PV is equal to 2 by 3 into m by 2 Na C mean square. Here what we have done is we have multiplied and divided expression 1 from by 2. So m by 2 Na C mean square is equal to 3 by 2 PV. Let us call this expression 2. The average kinetic energy of 1 gram molecule of a gas at absolute temperature T is given by average kinetic energy of a molecule is m by 2 Na C mean square is equal to 3 by 2 Na RT. Call this expression 3. Comparing equations 2 and 3, we get PV is equal to 2 by 3 Na into 3 by 2 kT, or PV is equal to Na kT, or PV is equal to RT, where R is equal to NaK. R is called the universal gas constant given by 8.31 joules per mole per Kelvin. So what have we done here? We have deduced the perfect gas equation from the kinetic theory of gases. PV is equal to RT is the equation of state for an ideal gas. Next, let us derive the most important gas laws from the kinetic theory of gases. The first law which we are going to derive is the Boyle's law. From the kinetic theory of gases, the pressure exerted by a gas is given by P is equal to 1 by 3 rho into C mean square. Instead of rho, let us write now m by V. This means that P is equal to 1 by 3 m by V C mean square. Let us transpose V to the left hand side of the equation. So we get PV is equal to 1 by 3 m C mean square. At constant temperature, C mean square is a constant. Thus, for a given mass of a gas, from the above equation, PV is constant at a constant temperature. Hence, what we have done now? We have derived the Boyle's law from the expression of pressure. So, we can see that Boyle's law can be derived from the expression for pressure, which was derived on the basis of assumptions of the kinetic theory of gases. And as everyone knows, Boyle's law is valid for ideal gases. Next, let us derive the Charles law. From the kinetic theory of gases, the pressure exerted by a gas is given by P is equal to 1 by 3 rho C mean square, or P is equal to 1 by 3 m by v C mean square, or PV is equal to 1 by 3 m C mean square, or PV is equal to 1 by 3 small m Na C mean square for 1 gram molecule of a gas at absolute temperature T. The mean kinetic energy E is equal to half m C mean square is equal to 3 by 2 kT. Thus we have PV is equal to Na kT. When P is a constant, we have V is proportional to a temperature, which is nothing but the Charles law. So when pressure is a constant, Avogadro's number is a constant, K is Boltzmann constant. So what we are left with is V is proportional to temperature. Next, let us derive the Regnolds law. As derived from Charles law, we have PV is equal to Na kT. When volume is a constant, then P is proportional to temperature. Thus, for a given mass of the gas, the pressure is directly proportional to its absolute temperature, provided the volume remains a constant. This is Regnolds law. So we have seen up till now, we can derive Boyle's law, Charles law and Regnolds law from the expression of pressure. This law states, next we will derive the Avogadro's law. This law states that at constant temperature and pressure, equal volumes of all gases contain the same number of molecules. Let N1 and N2 be the number of molecules of two different gases M1 and M2, their masses, and C1 and C2 be their respective RMS velocities. Since the two gases have the same pressure and for unit volume, the pressure of the gases can be written as P is equal to 1 by 3 M1 N1 C1 square is equal to 1 by 3 M2 N2 C2 square. Call this expression 1. As the temperature of the two gases is the same, there is no change in temperature when they are mixed. This is possible only if the mean kinetic energy per molecule in the two gases is the same. That is 1 by 2 M1 C1 square is equal to 1 by 2 M2 C2 square. Call this expression 2. Based on the equation 2, equation 1 reduces to the condition N1 is equal to N2. This is the Avogadro's law. So we have been able to prove Avogadro's law from the expression of pressure, which was derived from the assumptions of kinetic theory of gases. Next, let us prove the Dalton's law of partial pressure. Suppose we have a number of gases or vapors which do not react chemically. Let their densities be rho 1, rho 2, rho 3, and let their mean square speeds be C1 square, C2 square, C3 square respectively. Now let us put all these gases in the enclosure, same enclosure. If these are put in the same enclosure, all of them will have the same volume. Then the resultant pressure P will be given by P is equal to 1 by 3 rho 1 C1 square plus 1 by 3 rho 2 C2 square plus 1 by 3 rho 3 C3 square plus so on so forth. Here 1 by 3 rho 1 C1 square, 1 by 3 rho 2 C2 square and 1 by 3 rho 3 C3 square signify individual or partial pressures of different gases or vapors. If we denote these by P1, P2, P3 respectively, we get P is equal to P1 plus P2 plus P3. In other words, the total pressure exerted by a gaseous mixture is the sum of the partial pressures that would be exerted if individual gases occupied the space in turn. This is the Dalton's law of partial pressure. I hope you have understood all these laws, how these laws can be derived on the basis of a single expression for pressure, and how that expression for pressure can be derived from the assumptions of kinetic theory of gases. In the forthcoming lectures, I will be moving ahead. I will derive a few more laws. I will also be establishing the Maxwell's-Boltzmann law of distribution of velocities, as well as I will be telling you what is the principle of equipartition of energy. I hope you have understood today's lecture.